So I focus mainly on wastewater treatment and particularly the biological process of wastewater because I think it's very natural. We're just using the naturally occurring organisms to break down the organic matter. So definitely some waste, I would call them more benign than others. So the domestic waste is mainly organics and nutrients, which we still need to remove to recover the most important resource of all, which is water. But we also need to recover there's valuable material. And, there's lots of valuable energy, phosphorus, polymers even, that we can recover from this waste. But there's also more, I would say, challenging toxic waste that we're facing with increased modernization applications. We all heard about plastics, microplastics, nanoplastics, pharmaceuticals, personal care products, the forever chemical that's like everybody's talking about, PFAS, and it's everywhere. So these are kind of the challenging chemicals that we started to see not only in industrial facilities, but also wastewater treatment plants are conveyors. So whatever they receive, they can treat. Traditional treatment or conventional treatment didn't change really from the over 100 years. Activated sludge is celebrated 100 years, 10 years ago, and we're still working with activated sludge. I don't think anybody's driving the same car that was developed in the 1900s. Yeah. But our systems some of them, our majority of them are still based on the same concept. And they were never designed to really treat these new contaminants that we're seeing. And the more modernity that we're having, everybody wants their, I would say, Gore-Tex or their Teflon pans, that non-stick pans. Everybody likes their, waterproof rain jackets, their stain-repelling women cosmetics. Everybody wants the shiny lipsticks, the nail polish. All these products that we are enjoying are causing issues because we're seeing them more in the environment. So this is where my research is focused on trying to see how we can, first of all, understand more about their fate in the conventional systems. How are these microorganisms trying to degrade and to what extent we're removing them? And what are the new technologies and how we can improve the current systems to be able to tackle. And part of my research also understands the need for collaboration and interdisciplinary research. Many of the engineering work is not only focused on engineering. We need to understand the water governance. We need to understand regulations. We need to understand the social impact. So this is where part of my work is to also work with people from social sciences, microbiology, chemistry. All these parts get together.
Looks like you are working on many different topics. So let me catch few words from it, what you just described. Like you mentioned to wastewater treatment versus recovery. So yes, nowadays there is a big transition from wastewater treatment facilities to resource recovery facilities. If you want to explain to the audience what are the key motivation for that transitioning from a treatment to resource recovery? And what's the difference?
Yes, I think the idea itself is not new. It has been there, but it's the public perception that has been changing. So the treatment option is still there. We still need to do treatment. But in this circularity, we're working more towards, we're understanding that the earth has a very limited resource that we all share, but also there is a capacity to assimilate. So in the past, we would say the solution of pollution is dilution. We can't do this anymore. We can't keep, because the earth's assimilation capacity has been reached. So circularity in everything, we're no longer talking about a linear economy, we're talking about a circular economy. And part of it is how can we recover, reuse, upcycle, and wastewater is not different. The idea was, in the past, it was more socially and culturally, and maybe humankind was rejecting the idea that I can extract from a waste material something that I can make use of. Now we're getting more into the real need to recover. And we're understanding that while landfill is not, like, we need to understand what goes to the landfill. And just like maybe for those who don't understand, the landfill also have the issues of leaching to the environment, which goes back to us. So we need to limit what we need to send to this, to grave, and understand the idea of going back to cradle, start reusing stuff from, deal with these waste material as new products that we can. So the concept is not really new, it's the application and the more awareness that we're having that started to push this.
So what kind of resources or material that we can recover from the wastewater?
Other than water, which I explained, like 99.9% of the wastewater is water. So, and then we have pollutants X, Mr. X, that we want to remove, this toxic. But these are, like we said, nutrients. So nutrients are plant nutrients, nitrogen and phosphorus. So there's a lot of phosphorus, which we can be used as soil amendments or fertilizers, nitrogen as well, or ammonia, energy. You work with anaerobic digestion, and part of many facilities actually can at least, if not generate or can become a positive contributor, net producer with energy, at least can offset the heating, the electricity required for the plants. So energy is a big thing. And there are polymers that we can use in different applications. And there's many sources that actually can reuse the material itself as new adsorbents for removing contaminants. Box is rich with resources.
How your research, or let's say that how Dr. Hamza's research contributing to that resource recovery specifically?
My research focused on technology development. How can we develop a technology, prove the concept that is working in recovery, and look how we can scale up this technology and make it fit within the system. This water resource recovery facility, or WRFF, water resource recovery facility, the new name that replaced the treatment facility. So where would we fit in this? Because many of these facilities has been built for years and they still have their service life to be for more years. How can we fit in that? How can we optimize the treatment? How we can make the treatment work better, more environmental control, look at the climate, the impact of climate. So cold climate like Canada, how can we fit in this cold climate? Extreme weather conditions, we're all now seeing more the 100 years storm event. Are our facilities ready to adapt to the climate change? We're seeing it with the extreme weather conditions.
So you are developing technologies, and I'm aware that you are pioneering the biofilm-based technologies such as aerobic granular sludge, for example. So how is that technology can improve the wastewater treatment efficiency?
Aerobic granular sludge, and I would say like lay terms, is immobilization of bacteria. So microbial aggregation. Sorry
to cut you, but before you continue this one, can you maybe explain to the people, new researcher, what is the difference between granular sludge and maybe flux and maybe biofilm? And
definitely. So in a typical treatment process, we have different, we call them unit operations or unit processes. So some are physical, some are chemical, and some are biological or a combination. So bigger particles that can settle easily are removed by physical means like screens, bar screens, grit chambers like the sand, the rocks, the pebbles, all the gloves, all the stuff. And then we go through a sedimentation and then a biological treatment. And the main purpose of the biological treatment is to remove the organic material and the nutrients. Within these biological treatments, we have naturally occurring organisms, but we engineer the process. We make sure that we provide them with enough food and enough oxygen, because they are in the biological process in the secondary treatment mainly, although not always. It's an aerobic process, which means the bugs would grow in the presence of oxygen or free oxygen. So bugs start to multiply in a binary fission mode, which is 1 become 2, 2 become 4, and so on. And when they multiply, they start to form flux, which are still suspended cultures, we call them, because they are in suspension by this aeration mechanism. The problem with this is when particles are in suspension, or bugs in the suspension, after that we need to separate this bugs or this sludge from the treated effluent, which is the clean water that we will have subsequent tertiary treatments like disinfection. When I'm comparing granular activated sludge versus conventional activated sludge, is this formation of aggregates, so particles. So a particle that is very small, flux, and I'm talking about less than maybe 50 microns, very small particles, and we're making them bigger by self-aggregation, without a media, without an attachment. We all see biofilms. If you go to any place where, like next to the sink, a growth of this slime layer, biofilm, bugs will find a way to attach. What I'm working on is mainly making this microbial community aggregate without any media to attach. The benefit of that is now we're having different conditions. Different bugs needs different environment, but they also perform different functions. So some bugs are better in removing organics. Some bugs are actually working, or bacteria working on performing nitrification activities. Some bugs are working on accumulating phosphorus in their cells. So with aggregating different microorganisms together, they form a micro-community, micro-aggregates. So I have different conditions within a single granular particle that is somewhere between 200 microns, maybe up to 1 or 2 millimeters. And that with the bigger particles, they can easily settle. So I can actually separate them easier and in a much shorter time. And with the aggregation, they start to have more of them. So more biomass retention. And I'm thinking of them, these are my soldiers. This is what I'm having more of very specialized, very active biomass that are aggregated together. People work together better, same teamwork.
So how that is better than the conventional?
It's better in the conditions, first of all, where I'm having different functions. As I mentioned, conventional system can have only, I would say, don't want one type, but one function, which may be removing organics only. They are not good in nitrification and in denitrification, in phosphorus accumulation. When I have different conditions in one single system and one single tank, let's call it, they can perform different functions. So I can treat, first of all, different pollutants. I have more absorption sites, for example, for the new contaminants that we cannot be biodegraded, but they can absorb or stick to, kind of, these. Third, reduction in the footprint. So I now eliminate the need for another secondary clarifier or sedimentation tank to separate, and more capacity. So I can, this word that we use now, intensify, allow to have more treatment, whether in terms of flow or better quality of effluent with less space, resources, tanks, and energy as well. So that's the main, I would say.
I'm curious about that, the micro-contaminant, the different contaminant that can be absorbed or attached to that biofilm, because nowadays people are talking about the PFAS. What that EGS or those technologies has an advantages for, I'm not going to say not going to treat or destroy, but at least holding or separating the biofilms, the PFAS.
Exactly what you've just said. We had some research that my PhD student finished her PhD, and she worked on she selected certain PFAS compounds from the literature, and we started to work with them. I'm working with Dr. Roxana Suring from chemistry and biology with that. And what we found is AGS had 10 times more absorption capacity compared to activated sludge. So this is very promising. But we need to be careful when we are defining which PFAS, because we have so far 11,000 identified compound of PFAS. Some of them are short chains, some of them are long chains. So there's more affinity and more absorption for the longer chains PFAS, but the shorter chains tend to be soluble. So AGS was very good in capturing the long chain PFAS compounds and immobilizing them. We started to see certain microorganisms that are abundant in the PFAS contaminated wastewater compared to other. It's a big claim to say or claim any biodegradation at the moment, but we are hoping to continue working on, first of all, isolating these microorganisms and try to understand, are they there because they're more tolerant to toxic, or do they perform specific functions that can help us at least cleavage this CF very strong bond?
But for, I would say a typical engineer look at your description of the granular sludge versus the conventional flux. The granular sludge has higher size, which means lower specific surface area compared to the conventional flux. So how do you explain that the high efficiency of attaching or absorbing the PFAS on that granular sludge versus the...
Yes, I really like this question because it's counterintuitive. First of all, this is a porous structure. So you have different absorption sites. So the porosity acts. And again, the concept of multiplication is for bugs. So one bacteria cell become two, not one granule become two. So it's more of a sticking. Plus, bacteria, any living organism generate a waste material. For bacteria, they generate what we call extracellular polymeric substances. Part of this is kind of polymers that are sticky in nature. So they also tend to, and they are bacteria defensive mechanism. So in fact, we started to see a spike in the concentration of these bacterial byproducts when we introduce more of this toxic compounds as a defense. Bacteria wants to defend themselves, shield themselves. So this acts more as a trapment or immobilization of this. With the porous structure and more absorption side, again, with normal conventional activated sludge, the maximum concentration would be 3,000 milligram per liter. We were able to maintain up to 20 grams, 20,000. So you have more and porous absorption better, more resilience and retention. So you have more absorption sites in total compared. But when we conducted our experiments, we started to remove the concentration from being a limiting factor. So if we're using 4 grams of activated sludge, we're also using 4 grams of granular activated sludge. But the structure, the porosity, the interconnected channels that we have within the granular structure contributed to increasing the absorption of these toxic compounds to the aerobic granular sludge compared to the activated sludge.
So you would say it's like it's a good technology or compared to the conventional one, and multiple factors. You mentioned that, okay, for the emerging contaminant such as PFAS and even the efficiency, multifunctions. So what are the disadvantages, challenges?
First of all, I would say most, not all, aerobic granular sludge are cultivated in sequencing batch reactors, which require that you will have at least, I would say, a storage or an alternating tanks. Big municipalities prefer continuous flow mechanism because they receive water all the time. Or wastewater all the time. This is number one. And I'm saying most because there are some research and some actually full-scale implementation that has introduced different settling mechanisms to allow for continuous flow operation.
Okay.
This is one. Two, change is really hard, and it requires, there's very good examples of retrofitting or upgrading, but many of the facilities would prefer to build it from a green field or a new, which would need a new facility to be.
Which is very hard to convince the municipalities.
Exactly. And it's, it's over 25 years now in practice, but still 25 years in an industry that is still operating with over 100 years. It's hard to do the change.
There is any full-scale facility here in Canada?
No. Not in yet. Canada, but not yet. Hopefully, I think we had a good chance when I was in Calgary to build the first, I would say, demonstration project with the collaboration of the city of Calgary and in the Bonnie-Brook, and we're trying to revive this. I heard some rumors that there are certain municipalities here in Canada that are studying the feasibility, again, licensing and all these, I would say, issues are playing a key role in the...
There is any in the worldwide?
Yeah, there's many plants, and there are a lot of plants in the US. Like, definitely they started in Europe, and then they migrated. The other thing is the cultivation. It takes long to cultivate the aerobic granular sludge, and we've worked actually one of the project that I've worked on was actually to develop a technology for fast generation. Okay. And we submitted a patent for this along with Calgary Innovates. Good. So they started to kind of in Europe to I would say, overcome this by sending seeds from one plant to another. They started this project when they started also to transform to the US. But it was a big journey for the bugs where they had hiccups during but they were able to recover that. So now it's not a problem anymore because of the proximity. Now we can generally seed from a nearby plant or utilize one of the, I could say, we published this work to fast generate and store even the granules for a long period to become active that we can seed them, drying and reactivation. So it's and the nice thing about it is it's also been easy to, I would say, put it together with other technologies like membranes, so hybrid technologies, so aerobic granular sludge membrane bioreactors, or to augment physical chemical processes. So it's very, I would say, I always look at the treatment as a puzzle and a piece in a puzzle that you can start to, so this adaptability is a big thing that we're working on.